Hi, Michael. Thank you for coming for my presentation, which is the front-end part of my work on loop optimization inside the exascale computing project. So we do a lot of work on simulation of the universe, of protein folding, lattice QCD, and so on. And we try, as you can imagine, we want to make the most use of our supercomputers, meaning we want to optimize our programs that run of them. This one is as I said, the front-end part of my work. So how to tell the compiler to do a specific loop transformation. So I'm going to talk about how to represent loop transformations inside the Clang front-end. And after that, also from my experience from doing making an extension to the front end, because usually I work in the mid-end on the LLVM-IR and not on the Clang AST. But let's first go into the motivations why we do this. So you may have seen these compiler hints, such as pragma unroll, which you tell the compiler, please unroll the loop by a specific factor or full unrolling. The compiler can sometimes determine it by himself, but not always chooses the best options. That's just a hard problem, and it's just easier to tell the compiler, hey, use this, I know I have tested this works best, so please use this unroll factor here. And instead of writing the code, as you say, the bottom one statement is usually something longer, can be 1,000 lines. You just write it once and tell the compiler to apply the loop transformation instead of doing it yourself. So historically, there are a lot of these compiler hints, and every compiler supports a different set of loop optimization. Very often, they're incompatible to each other. So for instance, GCC, just in GCC 8, added an unroll pragma, but instead using pragma unroll, like other compilers, such as Clang supports, they do pragma GCC unroll. So, meaning syntactically incompatible with other compilers, you need some if-defs, whether it's depending on which compiler you're using, for the proper way to tell the compiler to use the correct unroll factor. What's often overseen here is that the order in which if you do multiple transformation, the order actually matters here. So if you do an unroll and loop reversal, depending in which order you apply them, you get different results. In this case, they look not that much different, but if you're really into optimization, you want just one and only one output and not give the compiler a choice between, in which order to apply the transformations. The current transformations Clang currently supports have some shortcomings shown here. You can theoretically write all these pragmas at the same time on the same loop. It's complicated to understand what they actually mean. I can tell you for this one, the pragma OMP SMD will just swallow all the other pragmas, and the other ones have no effect and won't tell you about it. Even if there's no pragma OMP SMD, the order in which they apply is undefined. So this is where I'm coming in, which I try to fix. One part of the fix is actually, as I mentioned, there are lots of different compilers supporting different syntaxes to actually standardize these syntaxes. In this case, I'm in this OpenMP standard committee to try to standardize these as part of OpenMP. So for instance, the pragma OMP tile will probably be part of the OpenMP 5.1 standard. And there might be more transformation coming in future standards. So for now, as long as OpenMP, the OpenMP standard has not been ratified with loop transformation, we kind of have to do something compiler specific. So my proposed solution is to introduce a new pragma, like pragma Clang transform, followed by the transformation, and using clauses like the OpenMP implementation does. This avoids the ambiguity we have you've seen before, And I gave up on trying actually reuse the proper Clang loop to make the syntax more better understandable and while still keeping the backwards compatibility. So I introduced a new one, and still, if they are added to OpenMP at one point, I want to try to use as much of the implementation as possible. There will still be semantic changes because prop-OMP prop-mas are usually applied regardless of safety. So if you add prop-OMP parallel 4, you are responsible that it executes correctly, and the compiler will apply this prop-ma even if the result of your computation afterwards is incorrect. So at the moment, I have a couple of patches under the reviews. You see at these addresses. They're interestingly not directly consecutive because while I submitted them somewhere at midnight, there was indeed someone in between adding another pass. I hurried up to get them uploaded before the dev conference because I wanted to get feedback from people more experienced in the front end. For what, if I did something conceptually wrong, I wanted to tell me. I haven't gotten any feedback on that part, at least, so I assume everything what I am telling here is correct. That was sarcasm. So, first, let's go into the specific part just for this loop transformation. So first, how do we represent loop transformation inside the front end? And the data structure I came up with is what I call a transform tree. So this is a loop nest of your code with loops nested in loops and loops inside. And then you apply a transformation on it. In this case, let's apply an unroll enzyme of that. The unroll enzyme will modify some of the loops, and you do point from the old structure, from the original loop structure to the new one, what it's transformed. This can be one part of the loop structure tree, but at the bottom, we can actually point back to the original nodes because they do not change. And if you have transformations on this inner loops, body loops, they actually do not affect the result, so we don't need to copy them. Once we have this transformation, we can actually have an order we want after unroll and NGM. Let's say we want to apply vectorize on the middle of the loops. Here we apply the vectorize and point from the previous node to the most recent loop after vectorization. That means after these actually have been applied, this is a data structure, but they actually represent this loop structure, which is the final form after the transformation. This representation is used first for diagnostics, telling you it's impossible to unroll and jam without having an inner loop. For instance, but also to disambiguate the order inside the code generation. So when passing this information to the mid-end, to exactly have one and only one defined order. So the structure in the patches looks like this. There's a class transform tree, which uses a curiously recurring template pattern, which I'm not going to explain here. Just assume you're doing it, but it's used twice, once in the code gen and once in the semantic analyzer, and both construct therefore can use this analysis about the order of the transformation. So if we point first to original AST node, so this is a for statement. For instance, it has the list of subloops, and also the successor as shown in this diagram. I like to show the slides. It shows like the overview over how it's going to generate it. In the end, we want to generate, we are at the IR generation at the end, and we want to generate loop metadata for LLVM to consume. So what's loop metadata? If we have, at the moment, we had this prop Clang loop vectorize enable on some loop, it will generate some MD nodes inside the bitcode file, which are attached to the loops ledge terminator with the information about, there's debug information, for instance. It points to, hey, where's this loop declared in the source code, and also this metadata about what transformations then apply. So I just I mixed up the transformation. It says vectorize enable. The bottom says unroll enable. This is not intentional. Sorry about that. But of course, it would say, for vectorize, it would say LLVM.loop.vectorize.enable. So what I committed already, which already in LLVM, is a way to how to convey an order of transformations in the metadata. And what I came up with is these follow-up attribute. So for instance, you see in this case 2 transformation applied to the loop. So first it's vectorization, after that it's unrolling. It's always, the Clang transform always applies to the output or the loop which follows on afterwards on it. So lexically reading, it's in reverse order, but I think this makes most of sense. So this case, it says first to vectorize, so LLVM.loop vectorize, follow vectorize. So it's saying after applying vectorization on the vectorized loop, apply the follow-up, in this case, metadata number 10. And metadata number 10 also gives an attribute what to apply, that attributes to apply on this loop up after vectorization. In this case, it says LLVM.loop.unroll.enable. It's also said something like LLVM.loop disable non-force, which should avoid that any other transformation goes in between. So if after vectorization it would apply loop distribution instead of unrolling, that's probably not intended. So this disable non-force avoids, hey, all the other classes, if you're not see your metadata there, don't do anything with this loop. And at the end, there's something similar. So after the unroll loop, you don't apply anything else, because if the user wanted to apply distribution after unrolling, they would probably also would have specified so. Apart from the unrolling, vectorization, distribution, and unroll and jam that are currently supported in LLVM, I have variant of poly, which applies more transformation than just those. So for instance, in contrast to the current parsed pipeline, it can apply them in any order. So the transformation in the current LLVM parsed pipeline are restricted by the order in which they are executed. So it cannot actually execute in all the orders. So this is something that can fix inside poly. In addition, I also have more passes that I do support: tiling, loop reversal, something like waypacking, loop interchange, and so on. So this concludes my part about the thing that's specific for the loop transformation, and I want to share my experience that I had there while extending the Clang with this thing, which actually touches all the layers within Clang, so would make maybe good a tutorial. There was, by the way, a tutorial yesterday already, which was useful to understand how the structure works. I'm going more into how to modify this, the structure and what you have to pay attention for. So. There was the overview of Clang, as I mentioned, the tutorial yesterday. There's an older talk already you can see on YouTube, Introduction to the Clang AST. Also relevant, my first Clang warning, extended. This is more specific, of course, just adding a warning to Clang, but I, of course, did this as well, specifically unroll and jam. If you put unroll and jam on a loop which has no inner loop, you can't really jam them. There's no loop. So this is my graphics for all the layers of Clang, which are relevant here. I did a few more. So the top one is the file manager. Start with the files, which are passed as memory buffers to the source manager. You can think of the source manager passing characters to the lexer, which converts it to tokens. The preprocessor does some transformations on the tokens and emits, again, tokens. You see actually the errors going from top to down because the control starts from the parser. The parser asks the preprocessor for tokens. The preprocessor asks Lexa for tokens. The Lexa asks the source manager for characters. And the file manager asks the operating systems for files. After the parser, so this is like a pull model. After that, the parser actually calls function of the semantic analyzer to do things, and the semantic analyzer creates an abstract syntax tree which is passed to the Clang front end. And the Clang front end, depending on what options you pass to Clang, like if you pass dash F syntax only, it doesn't do that. But if you want to emit some code, it passes it to the code generator. So first, the file manager, probably not that difficult to understand, is tested by typical unit test, G-test in that file there. We have the source manager, also tested as Unix test, also be a component in the component Clang basic. The source manager has something interesting, some interesting behavior, how it manages source. You may have seen this source location thing, which represents some source. Actually, it's one consecutive buffer you can think of, which actually starts some built-in. So some built-in definitions that are already defined by the compiler are in this built-in section of the source location, and appended afterwards is actually source file. If you include something, it's appended afterwards. So you have the source.h, and that points to, there's a function called getIncludeLog, points to the where it is actually included. And this contains the source file. So if you start parsing now, let's say the result of this one, what int main, open parent, closing parent, you would point from the token int, would has a function getLog, which points to the location in the source location in the source manager as int. The parents here as well. Something interesting happens if you do a macro expansion. In this case, another source file is appended to the source manager containing the expansion of the macro, and which then points to where it has been expanded from, at get expansion range, and the spelling log where actually this word appears there. So this thing is used by the Lexa, which gets the character and the source location and determines, what are the tokens to pass. Gets passed to the preprocessor, again tokens, and this is actually the component which will interpret the dash include and modify the source manager. So this is actually the part where I start modifying things. So we have something like a transform handler, which we can register. And then we get register in this case if for a specific a namespace. In this one, it would be the namespace Clang transform. And we would get notified called when the parser encounters this. For that one, we would like to add a new annotation token. So there we take annotation tokens for loop hints, so the Pragma Clang loop before for OpenMP, and we add to this list, we add our own tokens. So this is one of the most easiest things to do in Clang. Everything else gets a lot more complicated. So what happens in the preprocessor is what you do with this is you take the original list of tokens, Pragma Clang transform, and put it into some these annotation tokens, saying, this is the thing we have to pass later. Why don't we pass it here? Actually, this could be part of an underscore pragma string, and then the preprocessor would copy your tokens somewhere else as well. So we can't, it might be at multiple location there. What you do then again, you push back the new tokens, so the annotation tokens and your other tokens, back to the token stream, such that the parser, when it continues parsing, will read your new tokens. So to the topic, we are here in the parser receiving the tokens, and this is the code that reacts on finding this token. So we have this parsed statement or declaration after attributes, which is basically a lie because it's also parsed before attributes. But this is basically a huge switch statement, which for every possible token, kind of token you see in the token stream, do something. In this case, we had the case, we find our annotation token. And we start the, okay, we know the annotation token, we now can pass the inner between the begin token and the end token. This is here. This is like how it's typical looks. So it's, in this case, it passes. This is just some typical code there. It's not really functional, like you see multiple returns, but it can react on what it encounters. It can call other parser statements, which would be the inner statement. It can return an error, and also can call the semantic analyzer to react on something happens. I encountered a transformation directive. There's also some completion token, which I'm not going into. And we are landing in how to create an AST. Unfortunately, I don't have much time, so I'm going to very quickly go through this. So we have different nodes kinds. There's OpenAP node kinds, and this list is a table-gen file. This is at least some part. This is easy. We add our new kind of node kind to the table-gen file, and the table-gen will generate a lot of files here. It will, we still have to generate our own class to represent the token, which requires you to implement some functions like the begin log, end log, and the children you have. You have to pay attention here. This class is not allowed to have any vtable. It must be trivial destructible, so no vector in there. And actually, it's checked statically by static assertion in the statement if you violate this thing. If you have clauses, in my case, clauses are not statements, so they cannot just inherit from statements. You have to do a lot of stuff by yourself. For instance, you have not generated the table-generated def file, but I have my own handwritten def file, which I use to assign identifiers with kind of clauses, and also write the classes representing the clauses. You have to do some tricks because, again, you can have no vtable, so you do some kind of hand-rolled out virtual inheritance of virtual functions. And there is something, since you can't have a vector in there, if you have a variable number of children nodes, you need to extend it after your own objects using something called trailing objects. You can inherit from this thing. Another problem is if my class is not inheritor of statement, you can't return from the children iterator because that can iterate only over statements. So you need to do something else. For instance, for dumping the AST, you have to change the AST node traverser and tell you, hey, while iterating over your AST node, use also traverse these children here. And you actually have to do this in a lot of cases. So the output, if you do this, looks like this. You have the transform executable directive and the full clause, and actually the for statement that is a child of your AST node, but the full clause is not returned by children, so this is traversed by the AST visitors. Actually, I have to use a lot of these AST visitors, so it might be convenient to implement a visitor class to use in various patterns. And you need to use it, extend support for a class and a lot of other code. So for template instantiation, for dumping, we have that, unparsing, distillation, libclang, AST matcher. We actually come to this SEMA. For semantic transform, it actually creates your creates your AST node class. You with these act-on functions, for instance, act-on transform executable directive, it just instantiates your class. If you instantiate templates, you need to have another traverser called tree transform, which returns a new AST tree after having it instantiated, potentially with some changes, some template arguments are now known. So I'm going to skip the diagnostics engine. Also some changes, so to be at CodeGen. CodeGen basically is also a recursive descent approach. So it goes to the root node and asks child nodes, please generate code for you. So I also have a part for attributes. I'm going to skip that because I'm end of time. Sorry for rushing. I'm ready for your questions.
All right. Are there any questions? Okay. Oh, there's one person.
So in the syntax for the pragma, I think there was something on loop ID. You also specified the loop ID.
Yes, it's possible. The problem is for tiling, for instance, you say tiling, you consume 2 loops and output 4 loops. If you just add the pragma in front of it, you just apply this pragma on the outermost loop. But if you want to apply something on the other loops as well, you need to somehow refer to it. And the idea is you assign an ID to the inner loops and can refer to it using this loop ID. So for instance, you want to parallelize the outermost loop. Okay, you put the pragma in front of it. But you want to vectorize the innermost loop. In that case, you refer to the loop ID of the innermost loop.
Just to confirm, these pragmas for loop transformation, do you expect there'll be users that you put maybe 10 pragmas to just explicitly order the optimization applied to this loop in that particular order?
So 10, I'm not sure, but I myself went up to 6. 6 I did for matrix multiplication requires some things. I would have 7 if I would have added vectorize as well, but it would vectorize anyway, so I didn't need to add this pragma.
And this will work very nicely with the existing pass managers by forcing the particular order the user specify on that loop nest, right?
Yeah, right.
Okay, great.
Any other questions? All right. Let's thank our speaker again.